Hello everyone, welcome back to another video of Math 215. In this video, we should be looking at a few examples of how to evaluate integrals cleverly using the concept of Cauchy-Broussard theorem for simply connected domains. Okay, so given an example, say example 1. Okay, if C denotes any closed contour. They have not specified what contour to use. Any closed contour, okay? Remember, Cauchy-Broussard theorem works for any closed contours. Any closed contour lying in the open disk. Remember, for a contour to exist in a simply connected domain, it must exist entirely in the interior of the domain, okay? As in inside of the domain. It cannot exist outside. Or it cannot even exist partially outside. It has to exist fully inside of our domain. In the disk, modulus of z is less than 2. Then evaluate the following integral, okay? Z e to the power z over z squared plus 9 to the power 5 dz over the contour, any contour basically, okay? Any contour basically. Let's first define our domain, as in lying in the open disk. Aha, this is our domain. Let's draw our domain first. Okay, the complex disk, modulus of z is less than 2, is basically a circle, right? It's an open circle, so which is why I'm giving a dotted line. It's an open circle. It does not touch the points 2i or minus 2i, but it's near these points, okay? Minus 2. So this is our complex disk, and it's basically working as our domain. Okay, so now you can as you can see, this function, okay, forget about our domain for the time being, okay? Think about this function, okay? Looking at this function, you can see there's going to be discontinuities, okay? The numerator does not have any discontinuity. It has an exponential function as well as z raised to the power of 1. So there are no discontinuities. The numerator is not causing any problems. The problem is created by the denominator, okay? As in, clearly we can see, given a specific number z, we can easily make the denominator 0. Let's first find out the value of z that makes the denominator 0. As remember, anything finite or infinite, anything finite or anything finite in your numerator and anything infinite in your denominator will of course give you an undefined number, okay? And even if anything finite over the numerator and finite in the denominator, or 0 by 0, whatever, they're undefined values, okay? And working with them is a hassle. Okay. So we need to find out our points at z which causes discontinuities. Let's say in the brute force method to find, let's say we try to brute force our discontinuity, as in use the brute force method to get our discontinuity. Let's say directly claim the denominator to be 0 and then find out using handy-dandy algebra what our values of z should be to get 0 in the denominator, okay? So we have z squared plus 9 to the power 5 is equal to 0, okay? And it's simply, it's pretty simple. You have then z squared is equal to minus 9, okay? You can take the 5 to the power 5 out, just multiply fifth roots on both sides of the equation. Then evaluating z, taking square roots on both sides, you are left with z is equals to plus minus 3i. As in, our function here, this overarching function, evaluated at whatever contour, okay? Whatever contour, that contour has to just be inside our domain, okay? So, if these kinds of discontinuities occur, it's not a simply connected domain anymore. Because remember, your f of z has to be analytic over your entire domain, our domain being this disk. But herein lies the beauty of this problem. This problem states the discontinuities of this function will occur at plus minus 3i. Plus minus 3i, if I extend this plane, okay, plus minus 3i are points here. If it doesn't look linear, I'm sorry, but plus minus 3i are points here. As in, it's outside of our domain. And of course, according to the theorems that I've spoke about before, if your points are outside of your domain, then no contour, there doesn't have to exist a contour that must enclose points that are outside of your domain. Points inside of your domain has to be enclosed by contours, not outside. So we're safe, as in the points inside this domain will not cause any discontinuities. You can try and see. Because at max, this disk doesn't even touch 2i or minus twice i, let alone minus 3i and 3i. So, of course, then this function is analytic over our domain D, which is, as I repeat again, modulus of z, which is less than 2, the complex disk, which is entailed by that. So, since our function, this function, is analytic in our domain D, simply use Cauchy-Grusat theorem, and of course, it's any closed contour. It's a closed contour. It's analytic in our domain. So 0. Okay? Very easy answer. Okay. Now, let me just, of course, your contour could be many different things. They told you that C denotes any closed contour. Your contour could be this, your contour could be this, your contour could be whatever complicated structure you can think of, you can give it, as long as it's a closed contour and it has only finitely many intersections, you can apply Cauchy-Grusat theorem. Okay? Now, let me flesh out a few of the trivialities, then we'll be moving on to the next concept. Okay? Like, I just wanted to give a trivial example. Say it's not even an example. This is a trivial sort of something trivial, pretty trivial. Say an integral. Say you have an integral. You have an integral c e to the power minus z squared dz. Okay? Where C is a closed contour. C is a simply closed. Okay, this is closed contour. Okay? And the closed contour looks like this. A very complicated contour indeed. Okay, very complicated contour, but our choice of contour doesn't even matter here, right? Irregardless of the size of our domain, e to the power minus z squared, an exponential function, is analytic. It's an entire function, in fact, and an entire function is continuous everywhere around the complex plane, right? So, again, as was mentioned in the previous example, regardless of what the shape of our contour, if your function is analytic inside your domain and your contour is a closed contour, just write this. Simple as that. Remember to make sure that your function is analytic throughout your chosen domain. Okay? If it's not analytic, then you have to use other methods, which are going to come in future videos.